The morning of March 19, 1945. Petty Officer First Class Takeshi Yamamoto stood in the shadow of a damaged hangar at Kasumigaura Naval Air Station, northeast of Tokyo, staring at an aircraft that defied everything he understood about engineering philosophy. The Vought F4U Corsair sat before him like a captured dragon, its distinctive inverted gull wings reflecting the weak spring sunlight, its massive propeller scarred but intact. 3 weeks earlier, this machine had been shot down over Kyushu after sustaining severe engine damage from concentrated anti-aircraft fire. Through extraordinary effort and considerable risk, the Imperial Japanese Navy had transported the crippled beast to the mainland for technical examination. The pilot had bailed out over friendly territory, leaving his aircraft to carve a brutal path through a rice paddy, damaging the wings and fuselage but leaving the essential systems remarkably intact. Now, as Yamamoto approached with his measurement tools and notebooks, he understood why Vice Admiral Takejiro Onishi himself had ordered this evaluation expedited. This was no ordinary enemy fighter. This was a revelation wrapped in bent aluminum and powered by a heart that Japanese engineers could barely comprehend. The Americans had built something that shouldn't exist according to Japanese aviation doctrine. A fighter carrying the engine of a bomber, armored like a fortress, yet somehow capable of matching Japan's most maneuverable aircraft in combat. What Yamamoto didn't know as he placed his hand on the Corsair's cool metal skin was that this single aircraft, hastily patched with fabric and scavenged parts, would trigger one of the most sobering technical assessments in Imperial Japanese Navy history. The machine before him represented not just superior American manufacturing, but an entirely different philosophy of engineering, one that prioritized brute power and survivability over the elegant minimalism that had defined Japanese aircraft design since the 1930s. This captured Corsair would travel from battlefield to technical facility, where teams of Japan's finest aeronautical engineers would spend weeks dissecting its secrets, documenting its capabilities, and confronting uncomfortable truths about industrial capacity that separated their nation from America. The early afternoon sun cast long shadows across the damaged airfield as Japanese naval engineers from Yokosuka Naval Air Technical Arsenal gathered around the wounded Corsair. Unlike the Grumman Hellcats and Wildcats they had examined before, this was America's most feared carrier fighter, the aircraft that had established air superiority over the Pacific with a kill ratio that made Japanese commanders wince when intelligence reports arrived. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The Japanese had heard reports about the Corsair since its combat debut in February 1943 over Guadalcanal. Early intelligence assessments had been dismissive, reports from field commanders who considered any aircraft that couldn't match the Zero's turning radius to be fundamentally flawed. Most Japanese pilots believed their doctrine of maneuverability above all else would always prevail against American designs that seemed to value speed and firepower over grace. That morning at Kasumigaura, those assumptions began to fracture like airframes under excessive G-forces. Lieutenant Commander Hiroshi Matsuda was the first to climb onto the Corsair's wing root, careful not to disturb the temporary fabric patches covering battle damage. At 41 years old, Matsuda had overseen technical evaluations since 1939, examining everything from captured Soviet fighters to downed British Spitfires. He knew aircraft intimately, understood every compromise and challenge inherent in aeronautical engineering. As he peered into the Corsair's cockpit through the distinctive bubble canopy, Matsuda experienced his first shock. The pilot's position was spacious, luxurious compared to cramped Japanese fighter cockpits, where every centimeter was contested by fuel tanks and ammunition storage. The instrument panel was comprehensive, showing engine parameters that Japanese pilots rarely monitored because their aircraft lacked the sophisticated systems requiring constant oversight. Vision from the cockpit was extraordinary, the bubble canopy and raised seating position providing visibility that Japanese pilots could only dream about. Matsuda called down to Commander Yamamoto with words that would echo through Navy technical reports. This machine is built around pilot survival and combat effectiveness, not weight savings. Every design choice prioritizes keeping the pilot alive and functioning. It was a profound observation. Yamamoto climbed onto the wing beside Matsuda and conducted his own inspection. The wing construction impressed him immediately. These were not the delicate, fabric-covered wings of Japanese fighters. The Corsair's wings were solid aluminum, built like bridge girders, capable of carrying not just 6 heavy machine guns with abundant ammunition, but also bombs, rockets, and external fuel tanks. The distinctive inverted gull shape served multiple purposes. It allowed the massive propeller ground clearance while keeping the landing gear short and sturdy. It positioned the wing roots at optimal angles for attaching to the fuselage. And it created a distinctive profile that struck terror into Japanese pilots who had learned through bitter experience that engaging a Corsair in anything except ideal circumstances usually meant death. The capture of this particular Corsair came during desperate times for Japan. American carrier task forces were striking targets across the home islands with near impunity. Japanese air defenses, once fearsome, had been ground down through 18 months of attritional warfare that Japan's limited industrial capacity could not sustain. But this Corsair was different. Rather than attempt to make it airworthy for propaganda purposes or desperate combat use, orders came from Vice Admiral Onishi to transport the fighter to Kasumigaura intact for comprehensive evaluation. Someone in Tokyo understood that studying American engineering might reveal insights more valuable than one additional fighter that would likely be destroyed in its first mission. The Corsair carried Bureau number 82505, identifying it as one of roughly 10,000 F4U fighters, built by Chance Vought, Goodyear, and Brewster since production began in June 1942. The aircraft was relatively new, manufactured approximately 8 months earlier, with fewer than 300 operating hours on its Pratt Whitney R-2800 double wasp engine. Perfect for comprehensive technical evaluation by Japanese engineers who specialized in understanding enemy capabilities. The journey from crash site to test facility began immediately once Navy recovery teams secured the aircraft. The orders were explicit and unusual. Do not cannibalize for spare parts. This machine was destined for complete evaluation at Kasumigaura and potentially Yokosuka Naval Air Technical Arsenal, Japan's premier aviation research facility. The challenge of transporting the damaged Corsair to Kasumigaura provided the first lesson about American engineering robustness. The aircraft had to be partially disassembled, loaded onto rail cars, and transported nearly 200 kilometers through areas still occasionally targeted by American bombers. Japanese aircraft in similar condition would typically have been stripped for parts and abandoned. The Corsair's construction, however, made field repair surprisingly feasible. The wings folded for carrier storage, a feature that simplified transport. The engine, despite battle damage, could be secured and protected. The fuselage, though scarred, remained structurally sound. Even in its wounded state, the American fighter demonstrated engineering choices that prioritized maintainability and durability. 5 days later, the Corsair arrived at Kasumigaura under heavy guard, transported in sections that would be reassembled in a secured hangar. Lieutenant Commander Sato Nakamura, the engineering officer who would lead the technical evaluation, filed initial observations that reached Admiral Onishi's office within 48 hours. Before formal examination begins, preliminary assessment reveals construction philosophy fundamentally different from our approaches. This American fighter exhibits weight that would cripple Japanese designs, yet intelligence reports confirm performance exceeding our best interceptors. The engine displacement alone exceeds our largest bomber power plants. How the Americans achieve combat effectiveness with such mass challenges everything we understand about fighter design. From Kasumigaura, the Corsair was carefully moved into Hangar 7, a facility dedicated to examining captured enemy equipment. The building had served as an evaluation center since 1942, where engineers had studied everything from Soviet La-GG-3 fighters to American P-40 Warhawks. The facility was located in Ibaraki Prefecture, approximately 70 kilometers northeast of Tokyo, an area that had served as a naval aviation center since 1922, By March 1945, Kasumigaura remained one of the few facilities still capable of comprehensive technical work despite increasing American air raids and resource shortages. The Corsair arrived on March 24th, was carefully positioned on reinforced stands, and assigned evaluation number K-385, marking it as Kasumigaura property. Japanese engineers immediately began their methodical examination, knowing they worked against time. American bombers were ranging ever closer, and there was no guarantee the facility would survive the coming months. The Naval Air Technical Arsenal at Yokosuka had dispatched its most experienced evaluation team. Specialists from Nakajima, Mitsubishi, and Kawasaki aircraft companies converged on the captured fighter. They measured everything: wingspan dimensions, fuselage length, propeller diameter, armor thickness at every vulnerable point. They traced every control cable, examined every hydraulic line, studied every structural member. The measurements revealed a fighter that dwarfed Japanese designs in every dimension. The wingspan of 41 feet exceeded the zero by 5 feet. The length of 33 feet made it longer than most Japanese fighters. The empty weight of nearly 9,000 pounds was almost double the Zero's weight and significantly heavier than the latest Kawanishi N-1K Shiden. Yet American pilots flew this massive machine from aircraft carriers, operated it in ground attack roles carrying 2,000 pounds of ordnance, and still achieved air superiority against lighter, theoretically more maneuverable Japanese opponents. The Americans had redefined what a naval fighter could be. The armor protection system provided particularly uncomfortable revelations. The Corsair surrounded its pilot with steel plate. Behind his seat, a heavy armor plate protected against attacks from the rear. Beneath him, armor protected against ground fire. The windscreen was bulletproof glass over 2 inches thick. Even the oil cooler had armor protection. Petty Officer Yamamoto measured the main armor plate carefully, calling out dimensions to his assistant. Approximately 8 millimeters thick, angled for optimal protection. Our fighters carry 3 millimeters maximum, usually none. His voice carried disbelief tinged with professional admiration. The Japanese had chosen maneuverability over protection, accepting that pilots would die if hit. The Americans had chosen to protect their pilots, accepting weight penalties that seemed insane by Japanese standards, then engineered around those penalties with overwhelming engine power. The fuel system examination revealed technology that Japanese engineers had attempted and largely failed to implement effectively. The Corsair's fuel tanks featured self-sealing construction. When punctured by bullets or shrapnel, these tanks automatically sealed the holes through chemical reactions, preventing fuel leakage and catastrophic fires. Engineer Kenji Takahashi, a fuel system specialist from Nakajima, examined the self-sealing mechanism with intense interest. Multiple layers of vulcanized rubber and untreated crude rubber that swells when exposed to fuel. When projectiles penetrate, fuel contacts the crude rubber layer, causing expansion that seals the puncture within seconds. Takahashi had tested captured sections by deliberately shooting them with various caliber weapons. In every case, fuel flow stopped almost immediately as the self-sealing mechanism activated. Japanese fuel tanks, by contrast, typically burst into flames when struck, turning fighters into flying coffins for their pilots. The hydraulic systems presented another study in sophisticated American engineering. The Corsair used hydraulically powered systems for landing gear retraction, wing folding, flap operation, and wheel brakes. Each system featured redundancy and emergency backups that Japanese designs rarely incorporated. If the primary hydraulic system failed, emergency systems allowed the pilot to manually lower the landing gear through mechanical means, ensuring he could land safely. If hydraulic pressure was lost, mechanical linkages provided backup. Every critical system had contingencies, reflecting an engineering philosophy that assumed damage and failure, then designed solutions to maintain functionality despite problems. Lieutenant Yamada, who had been documenting structural details, summarized his findings during the evening briefing. Every system has redundancy. Every critical component has protection. The Americans design this aircraft assuming it will be damaged, assuming systems will fail, then engineering solutions to keep the pilot alive and the aircraft flying despite battle damage. Our philosophy has been to eliminate weight for maximum performance. Their philosophy is to ensure survivability. The results speak for themselves in combat. On March 26th, the evaluation team began examining the Corsair's armament: 6 Browning M2 heavy machine guns, 3 mounted in each wing panel. Each gun was 50 caliber, firing ammunition far heavier than the 7.7mm or even 20mm weapons on most Japanese fighters. Captain Tanaka Yoshiro, an ordnance specialist, measured the weapons and calculated their combined firepower with growing concern. 6 guns, each capable of firing approximately 850 rounds per minute. Combined rate of fire exceeds 5,000 rounds per minute. Each 50 caliber bullet weighs approximately 43 grams and travels at nearly 900 meters per second. In a 2-second firing pass, this Corsair delivers over 160 heavy bullets downrange. The kinetic energy alone can destroy aircraft even without explosive rounds. The Corsair's firepower advantage was approximately 5-1. A Japanese pilot who allowed the Corsair to bring its guns to bear, even briefly, faced devastating consequences. The Americans had built their fighter around the principle that the first burst should be decisive, overwhelming opponents with a volume of fire that no aircraft could survive. The gun sight system impressed every engineer who examined it. A reflector sight projected aiming information onto an angled glass plate positioned in the pilot's line of sight. The pilot could adjust the sight for different target sizes and ranges without looking away from his target. Combined with the aircraft's stability as a gun platform and abundant firepower, the system provided hit probability that Japanese pilots could only envy. By March 28th, the evaluation team had completed their preliminary external assessment and had begun the process of carefully removing cowling panels to expose the engine. Everyone present understood this would be the critical examination. The Corsair's performance, all derived from one source: the massive radial engine that represented American industrial capability at its zenith. When the cowling panels finally came away, revealing the Pratt Whitney R-2800 double wasp in its mounting, the assembled engineers fell into stunned silence. Commander Matsuda had seen many aircraft engines during his career. He had examined captured Soviet radials, studied British inline engines, and helped develop Japanese power plants from the Nakajima Sakai to the problematic Homar. Nothing prepared him for the R-2800. 18 cylinders, he finally managed, his voice barely above a whisper, though everyone in the hangar could hear him clearly. Twin rows of 9 cylinders each. This engine displaces 2,800 cubic inches. He paused, performing rapid calculations. That is 46 litres. Our most powerful fighter engine, the Nakajima Homar, displaces 36 litres and produces at best 1,900 horsepower under ideal conditions with water injection. This American engine is rated at over 2,000 horsepower continuously, with emergency power ratings exceeding 2,300 horsepower. Chief Engineer Nakamura began measuring the engine's physical dimensions, calling out numbers to assistants who recorded everything in detailed notebooks. Each cylinder measures 5.75 inches in diameter, with a stroke of 6 inches. The compression ratio appears to be 6.7-1. Gentlemen, this is not a fighter engine. This is a bomber power plant adapted for fighter use. As the team examined the R-2800's construction, they discovered layer upon layer of sophisticated engineering. The dual-stage supercharger, capable of maintaining sea-level power output at altitudes where Japanese engines gasped for oxygen. The intricate system of cooling baffles and cylinder fins that managed heat from over 2,000 horsepower. The fuel injection system ensures consistent performance through violent combat maneuvers. "Look at this," Nakamura said, pointing to the engine's mounting system. Vibration dampening built into every attachment point. Flexible mounts that isolate the tremendous forces from the airframe. The Americans have engineered solutions for problems we barely understand exist. Across the hangar, Lieutenant Sato's structural analysis team had removed several inspection panels along the fuselage, exposing the Corsair's internal framework. What they found challenged every assumption about appropriate construction methods for high-performance fighters. The primary structure consisted of heavy longerons and formers, all connected with thousands of rivets. Each rivet appeared machine-driven, uniform, and precise. The structural members were aluminum alloy, far heavier gauge than Japanese designers would dare use. The quality control throughout was exceptional. Every component showed consistent manufacturing standards. This aircraft was not hand-built by master craftsmen, Sato reported during the daily briefing. This came from an assembly line, yet the precision matches or exceeds our best workshop production. The Americans have mastered something we have not: mass production without quality compromise. This observation struck at a fundamental challenge facing Japanese industry. Japan's aircraft manufacturing relied heavily on skilled craftsmen performing intricate work by hand. The system produced excellent individual aircraft but limited overall production capacity. Training took years. Output remained constrained by available skilled workers, who were increasingly being drafted for combat duty. The Corsair, before them, represented something fundamentally different. Mass production at a scale Japanese industry could barely imagine, yet without the quality degradation that Japanese manufacturers experienced when attempting to increase output. The Americans had developed manufacturing processes that allowed relatively unskilled workers to produce precision components, then assembled those components into aircraft that functioned flawlessly. The armament team, meanwhile, had accessed the wing gun bays and stood silently before the 6 Browning M2 machine guns. Captain Tanaka, who had examined weapon systems captured throughout the Pacific War, looked at the installation with the eyes of someone confronting a fundamental mismatch. 50 caliber, he said quietly, though his words carried clearly in the hangar's acoustics. All 6 weapons are 50 caliber heavy machine guns. The ammunition capacity exceeds 400 rounds per gun, over 2,400 rounds total. Our fighters typically carry perhaps 600 rounds total across all weapons, mixed calibers, often including rifle-caliber guns that merely annoy American aircraft. The implications staggered everyone who understood aerial combat. A Japanese pilot engaging a Corsair had perhaps 5 to 8 seconds of firing time before exhausting his ammunition, assuming he survived long enough to use it. The Corsair pilot had over 30 seconds of continuous fire available, more than enough to destroy multiple opponents in a single engagement. And if the Corsair pilot conserved ammunition, firing in disciplined bursts as American doctrine taught, he could engage enemy aircraft throughout an extended mission without running dry. Tanaka examined one of the Browning guns more closely, noting its construction. The weapon is beautifully engineered. Every component appears designed for reliable function and ease of maintenance. The feed system is sophisticated yet robust. These weapons will function in conditions that would jam our guns. By March 30th, the propulsion team had completely removed the R-2800 from its mounting and positioned it on a specially constructed stand for detailed examination. Commander Matsuda spent that morning simply studying the supercharger assembly, photographing it from every angle, sketching details that cameras might miss. The device represented engineering sophistication that Japan's aircraft industry could recognize, but struggled to replicate at scale. The supercharger uses a 2-stage, 2-speed design, Matsuda explained during the afternoon briefing, his voice carrying the weight of professional understanding mixed with reluctant admiration. The first stage compresses incoming air. That compressed air is then cooled by an intercooler before entering the second stage for additional compression. This system maintains manifold pressure at altitudes exceeding 30,000 feet, possibly higher. The Corsair's supercharging system solved this problem through brute force engineering, compressing air until the engine believed it operated at sea level even when flying in the stratosphere. The Americans had identified a problem, then engineered a comprehensive solution without concern for the weight penalties or manufacturing complexity. Engineer Takahashi had disassembled one of the 18 cylinders for microscopic examination. The cylinder walls showed a crosshatch honing pattern that minimized friction while maintaining compression seal. The piston itself, forged from aluminum alloy, featured multiple ring grooves machined with precision that Japanese manufacturing facilities achieved only inconsistently, even under ideal circumstances. "The metallurgy is extraordinary," Takahashi reported, holding a piston up to the light. The piston appears to be aluminum silicon alloy with copper additions for strength. The rings themselves are steel, treated with some process that gives them exceptional wear resistance. "We have nothing comparable in our inventory." The connecting rods presented another revelation. Forged from steel alloy and machined to tight tolerances, each rod incorporated design features that reduced weight while maintaining strength. The bearings used materials Japanese engineers could identify but not easily source, given the increasingly desperate resource situation. That afternoon, Intelligence Officer Commander Watanabe visited the hangar with documents recovered from other captured American aircraft and prisoners. Among the materials was a technical manual for the R-2800 engine, painstakingly translated by Navy linguists over several weeks. Watanabe addressed Matsuda and the senior engineers with news that felt like physical blows. According to this manual, the R-2800 engine in this aircraft is rated for 2,000 horsepower at takeoff under normal conditions. For combat operations, the pilot can engage war emergency power through water methanol injection, temporarily increasing output to 2,300 horsepower or higher for brief periods. The engineers absorbed this information in silence. Japan's most advanced fighter engine, the Nakajima Homare used in the Ki-84 Hayate and other late-war designs, produced barely 1,900 horsepower under optimal conditions with water injection, and that was when the temperamental engine functioned properly, which was increasingly rare given manufacturing quality problems. The Americans had installed engines in their standard fighters that exceeded Japan's best efforts by 20% or more. "There is more," Watanabe continued, his voice carefully neutral. "This manual is dated September 1943. The Americans have been producing this engine for over 18 months. According to intelligence estimates based on captured documents and prisoner interrogations, Pratt Whitney manufactures approximately 1,000 of these engines monthly. 1,000 monthly. Japan's entire engine industry produced only 4,000 total engines monthly, and production was declining. A single American factory produced 1/4 of Japan's total output and produced engines of dramatically superior capability that apparently functioned reliably enough for mass deployment. The industrial chasm wasn't closing. It was widening, had been widening since Pearl Harbor, would continue widening until Japan's defeat became unavoidable mathematical certainty. The structural analysis team spent April 1st through 3rd meticulously examining every accessible aspect of the Corsair's airframe. Lieutenant Sato had developed something approaching obsession with the aircraft's design philosophy, recognizing it represented a complete rejection of Japanese engineering orthodoxy. He had prepared detailed drawings showing every structural member, every armor plate, every protected component. This philosophy succeeded when our opponents flew aircraft with similar characteristics. When we faced the Buffalo and Wildcat, our Zeros dominated through superior maneuverability. But against the Corsair, which accepts massive weight penalties to achieve superior protection, overwhelming firepower, and tremendous power, our fighters face impossible disadvantages. He paused, letting the implications settle across his audience. The examination of the Corsair's fuel system produced more uncomfortable realizations. The aircraft carried an internal fuel capacity of 370 gallons, providing remarkable range for a fighter. But when fitted with external drop tanks, as intelligence reports indicated American fighters routinely operated, the combat radius exceeded 800 miles, possibly more. 800 miles combat radius with drop tanks. The Americans achieved this while maintaining all protective features Japanese designers had eliminated to reach 500 miles. The hydraulic systems examination revealed engineering depth that Japanese aircraft typically lacked. The Corsair used hydraulic power for landing gear, wing folding, flaps, cowl flaps, and brakes. Each system featured redundancy built throughout. If the primary hydraulic pump failed, emergency hand pumps allowed manual operation. If hydraulic lines were severed, mechanical backups provided limited functionality. If all hydraulic power was lost, the landing gear could be manually lowered through emergency mechanical release. On April 6th, a delegation of senior officers from the Navy General Staff visited Kasumigaura to observe the captured Corsair. Commander Matsuda led the tour, explaining discoveries his team had documented over 2 weeks of intensive evaluation. The visiting officers walked around the partially disassembled aircraft in silence, their expressions revealing carefully controlled alarm. Vice Admiral Takejiro Onishi, who had personally ordered this evaluation, stopped before the exposed R-2800 engine. He had commanded carrier operations early in the war, had personally observed the transition from Japanese air superiority to desperate defensive operations. Now he stood before this American engine like someone confronting evidence of inevitable defeat. "What you have shown us today," Onishi said slowly, choosing words with evident care, confirms what combat reports have indicated for months. The Americans possess not merely numerical superiority, but qualitative advantages across multiple parameters. Commander, you have examined this aircraft thoroughly. I require your honest assessment. Can we build something comparable? Can the Japanese industry produce fighters like this? The question hung in the hangar's air, heavy with implications. Every engineer present knew the answer, though none wanted to articulate it in front of senior naval leadership. Matsuda spent that evening drafting his response, knowing it would circulate through Navy Command and possibly reach the highest levels of government. The truth resisted gentle articulation, but professional integrity demanded honesty. On April 7th, Matsuda convened his evaluation team to discuss replication possibilities comprehensively before submitting his formal report. The discussion would be frank, technical, and brutally honest about Japanese industrial limitations. "Gentlemen," he began, "we must assess whether Japanese industry could produce an aircraft equivalent to the Corsair. I need honest evaluations from each specialty area. We begin with propulsion." Commander Nakamura stood, his expression grave. "The R-2800 engine represents manufacturing capabilities we do not possess at necessary scale. The supercharger alone requires precision machining beyond our reliable capacity, especially given current resource constraints and workforce depletion. The metallurgy demands alloys we cannot produce in sufficient quantities. The quality control necessary to prevent catastrophic engine failures in a design this complex exceeds our industrial standards, which have degraded significantly as experienced workers are conscripted." He paused, gathering his thoughts. "Could we build one copy? Perhaps, with enormous effort over many months, diverting scarce resources from existing programs. Could we mass-produce them? No. Not without completely rebuilding our manufacturing infrastructure, which would require years we do not have, and resources we do not possess. Attempting to copy this engine would consume capacity better used maintaining current production, inadequate as that production is. The armament team reported similar conclusions. "The 50 caliber Browning machine guns are magnificent weapons," Captain Tanaka said. "Superior to our aerial armament in reliability, rate of fire, ammunition capacity, and destructive power. But replicating them would require retooling our entire weapons manufacturing base. The ammunition production alone would strain resources already stretched impossibly thin. And even if we could produce the weapons, our aircraft lack engines powerful enough to carry 6 of them with adequate ammunition and still perform competitively." Lieutenant Sato's structural analysis offered minimal hope. The aluminum alloys used throughout the Corsair's airframe show consistent quality and properties we struggle to achieve. The riveting precision, the manufacturing tolerances of every component, the quality control evident in every fitting and fastener, these reflect industrial capabilities that Japan's aircraft industry cannot match in our current circumstances, possibly could not have matched even before the war when our industry functioned optimally. This assessment aligned with classified intelligence reports that Matsuda had reviewed but could not openly discuss. According to estimates compiled throughout the war, American aircraft production for 1944 had exceeded 96,000 aircraft of all types. Japan's production for the same year had reached approximately 28,000 aircraft, and quality had declined precipitously as experienced workers were drafted, strategic materials became scarce, and Allied bombing damaged manufacturing facilities. But raw production numbers told only part of the story. The Corsair represented not just industrial capacity but industrial sophistication. Every component reflected a manufacturing system capable of producing complex machines to exacting standards at high volume. Japan's aircraft industry, by contrast, increasingly relied on partially trained workers using degraded materials to produce aircraft with inconsistent quality and declining performance. There is another critical consideration, Commander Watanabe added. Even if we could somehow replicate the Corsair's capabilities, the Americans have not remained static. This aircraft was designed in 1938 and entered service in 1943. It represents American engineering from over 2 years ago. Intelligence reports suggest American manufacturers are testing new designs, possibly including jet-powered aircraft. By the time we could field a Corsair equivalent, the Americans will have moved beyond this technology entirely. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The afternoon session focused on whether selective improvements could be incorporated into current Japanese fighters without requiring complete redesign. If full replication proved impossible, perhaps incremental enhancements could improve survivability and combat effectiveness. The armor system could be partially implemented, Sato suggested. Not to the Corsair's extent, which our engines cannot support, but improved pilot protection would increase survivability without catastrophic performance penalties. The self-sealing fuel tanks, if we can improve our manufacturing processes, would save pilot lives and keep damaged aircraft flying longer. Commander Nakamura shook his head slowly. Armor adds weight. Self-sealing tanks add weight. Everything the Americans have done assumes powerful engines capable of carrying heavy aircraft at competitive speeds. Without engines approaching the R-2800's capability, we cannot simply add these features without devastating performance penalties. The Corsair succeeds because every element functions as integrated system. The engine provides power to carry armor and fuel systems. The armor protects the pilot and engine. The fuel systems provide range. The structure supports heavy armament. Remove any element, and the entire system becomes less effective. Cherry-picking features without the foundational engine power will not work and might make our fighters worse. On April 9th, the examination entered its final phase. The engineers had documented every measurable aspect of the Corsair's construction. Now they attempted to understand how American pilots actually employed this formidable machine in combat, studying the aircraft's capabilities within the context of American tactical doctrine. Commander Watanabe had finished translating the Corsair's pilot manual, a detailed document that provided insights into operational procedures and combat tactics. The manual emphasizes the Corsair's strengths, he explained during the morning briefing: speed, diving capability, firepower, and survivability. American pilots are instructed to use altitude advantage to dive on enemy fighters, make high-speed firing passes, then zoom climb back to altitude using the aircraft's superior power. This tactical doctrine, often called boom and zoom by American pilots, exploited the Corsair's strengths while avoiding prolonged turning engagements where lighter, more maneuverable Japanese fighters held theoretical advantages. The strategy transformed air combat from a contest of pilot skill and aircraft agility into something resembling industrial warfare: systematic, methodical, and ruthlessly effective. The manual also describes bomber escort missions, Watanabe continued. Corsairs accompany American bombers from bases in Saipan and Iwo Jima to targets across Japan. The aircraft's internal fuel capacity of 370 gallons provides remarkable range. But when fitted with external drop tanks, as is standard procedure, the combat radius exceeds 800 miles, possibly approaching 1,000 miles under optimal conditions. 1,000 miles. Japanese fighters achieving half that range had been considered remarkable achievements, accomplished only by eliminating every protective feature and flying at economical speeds that made them vulnerable. The Americans had engineered fighters reaching anywhere in the Japanese home islands from their island bases, fighting over targets with fuel to spare, then returning home with sufficient reserves for multiple landing attempts if necessary. The cockpit examination revealed another philosophical divide between American and Japanese design approaches. Lieutenant Takeshi Sato, a veteran pilot seconded to the technical evaluation team, had spent 2 days studying the Corsair's cockpit layout, instruments, and controls. "Everything is designed for pilot efficiency and combat effectiveness," he reported, evident admiration in his voice. The instrument panel provides comprehensive engine monitoring: oil pressure, oil temperature, cylinder head temperature, fuel pressure, manifold pressure, supercharger settings. The American pilot knows precisely how his engine performs at all times, can monitor for problems, can adjust settings for optimal performance. Japanese fighter cockpits, by contrast, featured minimal instrumentation. Pilots were expected to sense problems through sound and vibration, to know their aircraft through experience and intuition rather than precise data. This approach worked when aircraft were simple and pilots extensively trained. But as designs became more complex and training time compressed under wartime pressures, the lack of instrumentation created difficulties. Pilots couldn't recognize engine problems until catastrophic failure occurred. They couldn't optimize performance because they lacked data showing what optimal meant. "The gun sight is particularly sophisticated," Sato continued. A reflector sight projects aiming information onto an angled glass plate. The pilot can adjust the sight for different target sizes and ranges without looking away. Combined with the aircraft's stability as a gun platform, the gyroscopic sight for rough aiming while maneuvering, and 8 heavy machine guns, the Corsair provides hit probability that Japanese pilots cannot match. More subtle details emerged from careful cockpit study. The layout positioned controls logically, with the most critical controls falling naturally to hand. The seat featured adjustment mechanisms allowing pilots of different sizes to achieve optimal positioning. The canopy design maximized visibility while maintaining structural strength. Even the cockpit ventilation system was thoughtfully engineered, keeping pilots comfortable in tropical heat and providing adequate visibility in all weather conditions. "The Americans have thought of everything," Sato concluded. "They have engineered this aircraft not just as a weapon, but as a complete fighting system that maximizes pilot effectiveness while minimizing pilot workload and fatigue. Our fighters demand constant attention and management." The Corsair allows the pilot to focus on fighting rather than simply keeping the machine flying. That afternoon, as engineers photographed and documented final details, Matsuda walked the hangar perimeter, studying the Corsair from various angles. The aircraft would not be made airworthy. Fuel shortages and the danger of misidentification made flight testing impossible, and skilled pilots who could safely fly an unfamiliar American fighter were desperately needed for actual combat operations. Instead, the Corsair would become a training tool, helping Japanese pilots understand what they faced, though Matsuda privately doubted such understanding would prove useful. "How did you teach pilots to defeat an opponent with overwhelming advantages in speed, firepower, protection, and endurance?" "You couldn't. Not really. You could only teach them to exploit fleeting opportunities and hope for circumstances favorable enough that superior numbers might compensate for inferior equipment." But Matsuda understood that no amount of study or documentation would bridge the gap this examination had revealed. The Corsair represented more than superior engineering. It represented an entire industrial and technological system that Japan could not replicate, could barely comprehend, and certainly could not match in the time remaining before the war's inevitable conclusion. On April 11th, Commander Matsuda began drafting his comprehensive technical report, knowing his findings would circulate among Navy leadership, aircraft industry executives, and possibly reach the highest levels of government. The report needed to be thorough, accurate, and carefully worded to convey harsh truths without inducing complete despair or appearing defeatist, which could have severe consequences given the political climate. He structured the document around key subsystems: propulsion, armament, structure, protection, and operational capabilities. Each section detailed the Corsair's specifications, compared them to equivalent Japanese aircraft, and assessed replication possibilities. The conclusions were uniformly discouraging but professionally stated. The propulsion section ran to 39 pages, including detailed drawings of the R-2800 engine, its supercharging system, and auxiliary components. Nakamura had contributed technical analysis that read like both engineering manual and admission of industrial inadequacy. The R-2800 represents at least a 5-year advancement over our current engine technology, he had written in his summary. Closing this gap would require fundamental improvements in metallurgy, precision manufacturing, quality control, and integration of advanced systems such as sophisticated supercharging and fuel injection. Under current circumstances, with resource shortages, strategic bombing damaging our facilities, and accelerating loss of skilled workers to combat conscription, such improvements appear impossible within any relevant time frame. Historical records from the United States Strategic Bombing Survey, compiled after the war's end, would confirm these assessments with brutal precision. American investigators examining Japan's aircraft manufacturing facilities in late 1945 found an industry in collapse, unable to maintain existing production levels, much less develop new technologies or improve quality. The gap between American and Japanese aviation capabilities had not narrowed during the war. It had widened dramatically, exponentially, irreversibly. The armament section of Matsuda's report focused on the Corsair's 650 caliber machine guns and their devastating effectiveness. Captain Tanaka had calculated the weapon system's firepower mathematically, and the numbers were damning. 6 guns, each firing approximately 850 rounds per minute, delivering over 85 rounds per second downrange. Each 50 caliber bullet weighs 43 grams and travels at approximately 880 meters per second, carrying enormous kinetic energy. In a 2-second firing pass, a Corsair delivers approximately 170 heavy bullets to the target area. This volume of fire can destroy enemy aircraft through kinetic impact alone, even without explosive or incendiary ammunition. Japanese fighters typically carried armament delivering perhaps 30 to 40 rounds per second of much lighter bullets, often mixed caliber. The firepower difference was approximately 3-1 in the Corsair's favor, and that understated the disparity because Japanese guns frequently jammed while the American weapons functioned with legendary reliability. The structural analysis section documented the aircraft's robust construction and extensive armor protection. Sato had included cross-sectional drawings showing armor placement, detailed photographs of construction methods, and comparative weight analyses. His conclusion articulated the fundamental design philosophy divide. Japanese fighter design has historically emphasized agility, maneuverability, and range, accepting reduced protection as a necessary trade-off. This philosophy succeeded when opponents flew aircraft with similar characteristics. Against the Corsair, which accepts substantial weight penalties to achieve superior protection, overwhelming firepower, and tremendous power, our fighters face severe disadvantages. The Corsair pilot can afford tactical mistakes. Our pilots cannot. The Corsair sustains damage and continues fighting. Our aircraft cannot. This asymmetry profoundly affects combat outcomes and explains the kill ratios intelligence reports document. By April 16, Matsuda's report exceeded 280 pages with another 80 pages of technical drawings, photographs, and supporting documentation. He met with Vice Admiral Onishi to present key findings before submitting the formal report through command channels. The Corsair represents a synthesis of overwhelming industrial capacity and sophisticated engineering, Matsuda explained, summarizing weeks of intensive analysis. No single component is necessarily beyond our theoretical understanding. We comprehend the principles of powerful engines, effective supercharging, armor protection, self-sealing fuel tanks, but the integration of these advanced systems, the manufacturing quality, the availability of strategic materials, and the fundamental design philosophy reflect capabilities that Japan cannot match. Onishi listened intently, occasionally asking questions about specific technical points. Finally, he spoke with the weariness of a professional officer confronting unpleasant reality without political delusion. "What you are telling me, Commander, is that we face an opponent who can deploy weapons we cannot counter effectively and cannot replicate. You are telling me that the industrial and technological gap makes victory impossible through conventional means." "I am telling you what the evidence shows," Admiral Matsuda replied carefully. "The Corsair is not an exceptional aircraft by American standards. Intelligence reports indicate they deploy multiple fighter types of comparable or superior capability in substantial numbers. They produce over 1,000 Corsairs monthly, and this is only one of several fighter types in production. They can afford to lose these aircraft in combat and replace them immediately. We cannot sustain our current production rates, and the aircraft we produce are increasingly inferior to American opposition." The conversation turned to what lessons Japanese designers might apply to improve existing aircraft within the severe constraints of Japan's deteriorating situation. Matsuda outlined modest possibilities. Slightly improved armor protection that wouldn't catastrophically impact performance, better cockpit layouts to reduce pilot workload, enhanced gun sights to improve hit probability, but these were marginal improvements that could not fundamentally alter the technological imbalance. As April turned to May of 1945, the captured Corsair remained at Kasumigaura, now serving as a teaching tool for intelligence officers and combat pilots. Pilots transitioning to homeland defense operations would visit the hangar, studying the aircraft they would face, learning its capabilities and searching desperately for exploitable weaknesses. Most came away sobered. Experienced pilots who had fought throughout the Pacific War looked at the Corsair and recognized what it represented, not just a superior aircraft, but evidence of an unbridgeable industrial and technological chasm. The younger pilots, products of abbreviated training programs and knowing only what propaganda had told them, sometimes reacted with disbelief, struggling to accept that their adversaries possessed such overwhelming advantages. Lieutenant Sato often served as an informal guide for visiting pilots, explaining the Corsair's systems and capabilities. He had flown Zeros in combat, had engaged American fighters over the Philippines, and had survived experiences that taught him brutal lessons about industrial warfare. "The Corsair's greatest weakness is also its strength," Sato would explain to each new group. "It is not particularly maneuverable compared to our fighters. In a low-speed turning fight, a skilled pilot in a Zero or Hayate can theoretically outturn it. But Corsair pilots do not fight that way. They maintain speed and altitude, using superior power and protection to dictate engagement terms. They dive, attack, climb, away. Our fighters cannot follow them in the climb because we lack engine power. We cannot catch them in the dive because they are faster and structurally stronger. And if we somehow manage to inflict hits, their armor and self-sealing tanks keep them flying while a single burst from their guns destroys our aircraft." This tactical reality had transformed the Pacific Air War by May 1945. American fighters operated with near impunity over Japanese-held territory, escorting bombers to targets across the home islands, intercepting Japanese aircraft at will, and returning to base despite often heavy damage. Japanese fighters, increasingly outnumbered and outperformed, achieved occasional victories through desperate tactics or fortunate circumstances, but could not alter the strategic situation. By late May, Matsuda's comprehensive report on the captured Corsair had circulated through Navy leadership and aircraft industry executives. The document's impact proved both profound and futile. Profound because it definitively demonstrated the technological and industrial superiority that doomed Japan's war effort. Futile because this understanding came far too late to alter the war's trajectory, and Japan lacked the resources to apply the lessons even if time had been available. Engineers at Nakajima, Mitsubishi, and Kawasaki received copies of the technical analysis. Some attempted to incorporate minor improvements into existing designs, slightly better armor protection, improved instrumentation, refined cockpit layouts, but as Nakamura had predicted, without fundamentally more powerful engines, these incremental enhancements could not bridge the capability gap and often made performance worse by adding weight that Japanese engines could not effectively carry. Throughout June and into July, as American B-29 superfortresses continued devastating Japanese cities and industrial infrastructure, the captured Corsair remained at Kasumigaura, a silent monument to industrial disparity. Air raids damaged the base multiple times, but the hangar housing the Corsair somehow survived, the American fighter emerging unscathed from attacks by its own nation's bombers. On August 6th, the atomic bomb destroyed Hiroshima. 3 days later, a second atomic weapon devastated Nagasaki. On August 15th, Emperor Hirohito announced Japan's surrender in a radio broadcast, his voice trembling as he informed his subjects that the war situation had developed not necessarily to Japan's advantage, a phrase that would become infamous for its euphemistic understatement. Commander Matsuda heard the Emperor's broadcast in his office at Kasumigaura. He thought of the Corsair sitting in its hangar nearby, thought of the hundreds of pages of technical analysis he had supervised, documenting in meticulous detail the reasons for Japan's defeat, thought of all the careful measurements and drawings that illuminated the path to inevitable conclusion. Understanding the enemy's capabilities had not provided victory. It had merely illuminated the magnitude of Japan's industrial and technological inadequacies. Knowledge without capacity to act on that knowledge was simply awareness of futility. In the weeks following surrender, American occupation forces arrived at Kasumigaura. Engineers from Chance Vought and Navy technical intelligence teams came to see their own aircraft through Japanese eyes. They reviewed Matsuda's report with professional interest, impressed by its thoroughness and accuracy despite the limited tools and desperate circumstances under which it had been produced. "Your technical analysis is exceptionally comprehensive," remarked Commander William Henderson, an American engineer specializing in naval fighters. He spoke through a translator to Matsuda during one of several post-war interviews. "You understood the Corsair's capabilities very accurately. Did this understanding help develop effective countermeasures?" Matsuda smiled sadly. "We understood what we faced, Commander. Understanding and countering are entirely different things. Your aircraft represented industrial and technological capabilities that Japan could recognize but not match. The Corsair was not merely a superior fighter, it was evidence of a contest we could not win." Historical analysis in the decades following the war would confirm Matsuda's assessment with exhaustive documentation. The Pacific War had been fundamentally a conflict between incompatible industrial systems. American manufacturing capacity, technological sophistication, resource access, and systematic approach to mass production had enabled weapons development that Japanese industry could not effectively counter. The captured Corsair had provided Japanese engineers with a detailed blueprint of their disadvantage, but blueprints alone could not overcome fundamental industrial and technological disparities. Japan's skilled engineers had documented the gap with scientific precision. But understanding a problem and possessing the capacity to solve it were entirely different challenges, a lesson learned at devastating cost. The captured F4U Corsair was eventually destroyed by occupation forces, cut apart and scrapped along with thousands of Japanese aircraft as part of disarmament procedures. But the aircraft's legacy persisted in the detailed technical documentation preserved in Japanese and American archives. Matsuda's report, declassified in the 1960s, provided historians and aviation researchers with unique insights into how capable engineers from an industrialized nation assessed and understood enemy technology during wartime under desperately constrained circumstances. In post-war memoirs written in the early 1950s but not published until decades later, Matsuda reflected on the experience. We examined the Corsair with professional thoroughness and reached professional conclusions. The aircraft taught us that wars are won not merely through courage and spirit, though these matter greatly, but through industrial capacity and technological sophistication applied systematically at scale. Japan's warriors fought with extraordinary dedication, achieving remarkable successes through skill and determination. But dedication cannot overcome the physics of engine power, the mathematics of firepower disparity, or the metallurgy of armor protection. We learned these lessons examining an enemy's aircraft while our nation burned. The cost of that education was comprehensive defeat. If you enjoyed this deep dive into history, please hit the like button, share this story with fellow history enthusiasts, and subscribe for more detailed historical content. Your support helps us bring these stories to life.